Welcome. So, in microeconomics, every single firm, whether it's a giant manufacturer or a local bakery, faces one fundamental, inescapable problem. How exactly do you allocate your scarce resources to achieve the maximum possible profit? Honestly, it's the core of what we do as economists. Today, in this explainer, we're going to look at a highly effective mathematical tool used to solve that exact optimization problem. Here is our agenda for today. First, optimizing under scarcity. Then, formulating the LP model, the graphical solution, shadow prices and duality, and finally, a summary and key takeaways. Section 1. Optimizing under scarcity. Okay, let's dive right in. Because resources aren't infinite, tough decisions have to be made. To make those calculated decisions, economists use something called linear programming, or LP. Essentially, it's a really powerful mathematical optimization technique. We use it to determine the absolute best possible outcome, whether that means maximizing our profit or minimizing our costs, specifically in situations where our constraints take the form of strict linear relationships. It literally forms the foundation for understanding firm behavior, input-output analysis, and how to properly allocate resources. Section 2. Formulating the LP model. So, knowing what it is, how do we actually build this mathematical model to solve the problem of scarcity? Well, every linear programming model we formulate in economics is built by stacking together four fundamental, necessary components. First up is the objective function. This is the linear function we want to optimize, like total profit. Second are decision variables. These are the economic variables the decision maker actually controls, like how much of a certain good to produce. Third, the constraints. These represent our very real physical or economic limits on resources. And fourth, the non-negativity conditions. Because, let's face it, in the real world, you simply can't produce a negative quantity of a product. Let's look at a tangible business case to see how these four components actually come together for a competitive firm trying to make the most of its limited labor and capital. Our objective function is to maximize profit, which we'll call Z, where we make $50 for every unit of good one we produce and $40 for every unit of good two. But here's the catch. Look at our constraints. We only have a maximum of 40 hours of labor available, giving us our labor constraint equation. We also have a maximum of 120 machine hours, which gives us our capital constraint. And, of course, our non-negativity constraint means the production of goods 1 and 2 must be greater than or equal to 0. Section 3. The graphical solution. Now, looking at a table of algebraic equations is one thing, but the absolute best way to understand these abstract mathematical constraints is visually, and this brilliantly illustrates what those equations mean in practice. Here, the blue line represents our labor constraint, and the orange line represents our capital constraint. See that gray shaded area bounded by these lines and the axes? That is what we call the feasible region. It's like a giant sandbox of possibilities. This polygon represents all the reachable, possible production combinations based on the firm's strict labor and capital limits. Any point inside that gray area satisfies all of our constraints simultaneously. But how do we find the absolute optimal choice within that region? The steps are actually pretty straightforward. Step 1, identify that feasible region, which we've just done. Step 2, find the corner points. This relies on the fundamental theorem of linear programming, a real game changer of a concept stating that an optimal solution will always lie at a vertex or corner point of the feasible polygon. Step 3, evaluate our objective function at those specific corner points. That means we literally just test the coordinates at 0, 0, 30, 0, 0, 20, and that very interesting intersection of our two binding constraints at 24, 8. And here is the ultimate payoff. When we test those vertices in our objective function, or if we shift our dashed or ISO profit line outward until it just touches the very edge of our feasible region, we get our answer. The firm maximizes its profit at exactly $1,520. How? By optimally allocating its resources to produce exactly 24 units of good 1 and 8 units of good 2. We've mathematically solved the optimization problem. Section 4. Shadow prices and duality. Now, as economists, we always have to ask the classic question, so what, right? Finding the maximum profit is a great result, but it isn't the end of the story. Understanding exactly why a resource is valuable internally to the firm is the real economic takeaway here. Linear programming offers profoundly deep economic insights through this concept of duality. On one side, we have the primal problem, maximizing profit given fixed resource constraints, which is exactly what we just did. But every primal maximization problem is intrinsically linked to a hidden corresponding dual problem. The dual problem seeks to minimize the total imputed cost of resources, ensuring that the implicit value of the resources used equals or exceeds the profit derived from producing the goods. They are essentially two sides of the exact same LP coin. The optimal values we get from solving that dual problem are known as shadow prices. The shadow price represents the marginal economic value of acquiring one additional unit of a constrained resource. So the absolutely crucial point is this. If the shadow price of labor for our firm is $2, it means that acquiring just one additional hour of labor will increase our maximum total profit by exactly $2. This is incredible because it provides a direct analytical link between linear programming and marginal analysis in microeconomic theory. It tells a manager exactly how much they should value and be willing to pay for more resources. Section 5. Summary and Key Takeaways. Okay, let's bring all this theoretical math and applied economic theory together for a quick review. Here are the key takeaways from today's explainer. First, linear programming allows economists and business managers to efficiently optimize a linear objective under strict real-world constraints. Second, thanks to the fundamental theorem, we know the optimal solution always occurs at a vertex of the feasible region, which massively simplifies our search. And third, the dual variables yield shadow prices, giving us the marginal value of our resources. By mapping out that feasible region and carefully examining shadow prices, firms are empowered to make highly efficient, data-driven decisions on both their production targets and their resource procurement. To wrap up, I want to leave you with this provocative thought to ponder before our next session. If shadow prices tell us the internal value of our constraints during a profit maximization problem, how do they guide our decisions when our firm's sole objective is cost minimization? Think about how that dual relationship flips. We're going to pick it up right there with practice problems next time. Keep optimizing.